A reflection is often referred to as a flip in a plane. Now, while that term may not sound very mathematical, why do you think that term might be used? Well, to help you answer your lesson question, how are reflections described mathematically? Next, you're going to explore the properties of reflections. In this lesson, you're exploring a rigid transformation, a reflection. Now, in a reflection, all points of the pre-image are reflected across a line of reflection to produce the image. So here we have an example. Triangle ABC is reflected across line EG to become the image, triangle A prime, B prime, C prime. So we can write this mapping. Triangle A, B, C maps to triangle A prime, B prime, C prime. That also means that each point in triangle ABC maps to exactly one point in triangle A prime, B prime, C prime. So point A maps to A prime, B maps to B prime, and C maps to C prime. And any other point in triangle ABC can be mapped to exactly one other point in the image. Now you're going to explore properties that define a reflection.
Let's take a look at the formal definition of a reflection. A reflection is a transformation such that the line of reflection is the perpendicular bisector of the line segment connecting a point in the pre-image with its corresponding image. And any pre-image point that lies on the line of reflection is mapped to itself. We can break this definition down by taking a look at an example. The first part of the definition is talking about the line segments we can make by connecting a point in the pre-image with its corresponding image after reflection. For example, if I connect point A in the pre-image to point A prime in the image, then I'll have line segment A prime. It's the same if I take point B in the pre-image and connect it to B prime. Remember, the definition we just looked at says that the line of reflection will be a perpendicular bisector to these line segments. And of course, that means these line segments are perpendicular to the line of reflection. Another thing it means is if I look at where the line of reflection intersects these line segments, points L and J are the midpoints of their line segments. If we want to be formal, we can say that point L is equidistant from point B and B prime, and J is equidistant from A and A prime. And that'll be true for any point in the pre-image. For example, I could look at point H in the pre-image, connect it to its corresponding point in the image, H prime, and I have another line segment. Again, this line segment will be perpendicular to the line of reflection. And again, the intersection point is going to be equidistant from H and H prime. Another thing to keep in mind is that because all of these line segments are perpendicular to the line of reflection, all of these line segments are also parallel. Now, the second part of the definition is pretty quick. Any pre-image point that lies on the line of reflection is mapped to itself. That just means because point C is on the line of reflection in the pre-image, it's going to be in the same location in the image. So the same point is going to be marked as C prime.
we know that rigid transformations, like reflections, preserve size and shape. Reflections also preserve segment lengths. So in this example here, that means that all the line segments in triangle JKL will be congruent to corresponding line segments in J prime, K prime, L prime. So JL is congruent to J prime, L prime. JK is congruent to J prime, K prime. And LK is congruent to L prime, K prime. Reflections also preserve angle measures. So that means that angle LJK is going to be congruent to L prime, J prime, K prime, that JKL will be congruent with J prime, K prime, L prime, and that JLK will be congruent to J prime, L prime, K prime. Now keep in mind that reflections do not preserve orientation, unlike some other rigid transformations. Now orientation means we're talking about the order of the vertices. So for example, if I begin with our pre-image at point J and move clockwise, I have points J, K, L. If I do the same in the image and begin with J prime and move clockwise, I have J prime, L prime, K prime. They're not in the same order. They're almost in reverse order. So that might help you to connect to why the reflection of the word ambulance appears on the front of that vehicle. So now, see if you can identify properties of reflections. You're still working to answer the lesson question, how are reflections described mathematically? Well, now you've developed a formal definition for a reflection and explored the properties of a reflection. Now, when a reflection takes place in a coordinate plane like this one, then you can use coordinates to describe the reflection. So let's investigate that next. You may have noticed a pattern when reflecting across the x-axis. In fact, there is a general rule you can follow anytime you reflect across the x-axis. The x-coordinate will remain the same, and the y-coordinate is negated. Let's take a look at this rule using transformation notation. The rule for reflecting across the x-axis is this. Begin with a lowercase r that represents a reflection, and then a subscript x-axis that tells us what the line of reflection is. That's followed by a coordinate pair. This represents the input, or in this case, the pre-image point. This arrow means maps to, and then it shows the output, another coordinate pair. In this case, it's going to be the image point. Now that we have this rule, let's see if we can apply it to the example here. So I'm going to begin by applying this rule to point B in the pre-image. So to use the rule, I'm going to begin with an R to tell me that I'm going to reflect across the x-axis. And my input is going to be point B, which is located at -1, 5. That's going to map to the output point. Now the output is going to be at B prime, and if I follow the rule, I know that the x coordinate will remain the same, so I'm going to leave this as -1, and the y coordinate is going to be negated. So I'm going to take that 5 and make it -5. So since I have the reflection already on the coordinate plane here, I can see that B prime is indeed located at -1, -5. So this rule does hold. Now you're ready to determine the image of a vertex. Now let's determine a rule for when a reflection happens across the y-axis using this example. Now note that these two trapezoids actually overlap each other, and that's okay. That occurs whenever the pre-image is intersected by the line of reflection. So let's begin by taking a closer look at all the vertices. Now point K in the pre-image maps to point K prime, and K prime is located at 1, 3. Point L in the pre-image maps to L prime, and L prime is at -1, -2. Same if we look at M, which maps to M prime, and M prime is at 4, -2, and N maps to N prime. N prime is at 2, 3. So now let me take a closer look at these points. I'm noticing a pattern. I can see that in each of these points, the y values remain the same, but the x values are negated. So with that in mind, I can now create a rule. So let's complete the rule here. The rule for reflecting across the y-axis is that the point input xy will map to -x, y. Now you're going to use a given reflection over the line y equals x in order to determine a general rule. Keep in mind that you can reflect across any line on a coordinate plane. In this lesson, we're just going to focus on the most common. Let's take a look at the rule for reflecting across the line y equals -x. Now, if I compare the input coordinate pair to the output coordinate pair, I can see that the x and y coordinates are switched and that they're both negated. So with that in mind, I'm now going to see if I can reflect triangle ABC across the line y equals -x using this rule. So let's begin by looking at point A in the pre-image. So A is located at -4, -5. Now I need to map that to point A prime. And using the rule, I know that I need to, first of all, switch the x and y coordinate. So I have -5, -4, and I need to negate each. So that means that A prime is 5, 4. Let me go ahead and add that to the coordinate plane. Great, let's take a look at point B. Now I notice that point B is on the line of reflection. That means that it's going to map to itself. But let's apply the rule just to make sure that it holds true. So B is located at 1, -1. It's going to map to B prime, and I can do that by switching the x and y coordinates. So I have -1, 1, and then negating each. That results in, well, 1, -1. It's the same point, which I expected. So I'm going to label that point B prime. And finally, point C. Point C is located at 1, -5. We're going to map to C prime, which is located at 5, -1. I figured that out by switching the x and y coordinates and negating each based on the rule. So I can add that to the coordinate plane, and I just need to connect these points together so that I can see my image and the result of the reflection. Let's also take a look at another example using a reflection over y equals negative x. Now, I want you to keep in mind that you should always pay special attention to the terminology. And in this case, we should do that particularly with this question. Rectangle Q prime, R prime, S prime, T prime was created using the rule that's given here. Graph the pre-image of the figure. Now, did you notice? I need to graph the pre-image of the figure. I'm given the image. I know that because of the prime notation. So in this case, even though I'm given the rule for mapping from the pre-image to the image, I need to actually work backwards to figure out what the pre-image is. So let's begin by putting our line of reflection on our coordinate plane. So the rule says it's for y equals negative x, so I'm going to go ahead and add that line here. It's a line with a slope of -1 that goes through the origin. Now, let me begin by looking at point Q prime. Now, because this is point Q prime, that's where this rule maps to. So I'm actually going to add it on the right here. And I see that Q prime is at -2, 4. I need to work backwards to figure out what point Q is in the pre-image. Now, the rule tells me that I need to switch the x and y coordinates and then negate each. So I'm going to do that in the opposite direction. I'm going to negate each, so I have 2, -4, and then I'm going to switch those two coordinates. So that means Q is at -4, 2. All right, let me go ahead and add that to the coordinate plane. All right, let's take a look at the next point, R prime. So again, R prime is where this rule maps to, and R prime is at 4, 4. I'm going to work backwards, so I'm going to negate both coordinates, and then I'm going to switch them. If I do that, I'm going to get R, which is located at -4, -4. If I add that right here, I just have another point I need to find. So I'm going to start with S prime. So S prime is located at 4, 2. I'm going to work backwards to find point S. So that means if I negate 4 and 2 and then I switch them, I'm actually going to be left with -2, -4. I'm going to add that as well. Now, I don't need to work on T prime. And that's because I notice that T prime is actually on the line of reflection. That means that point T will map to that point. So I can just label this as point T as well based on what I know about reflections. So I now have my points. I just need to connect them together. And now I have the pre-image for this reflection. So again, remember to pay special attention to terminology, whether you're trying to find the pre-image or the image. Now, you may have noticed that the act of negating two values and then switching them, or switching to two coordinates and then negating them, is really the same regardless of the direction. However, there are other rules for reflections where the order is very important. So make sure you pay special attention to your rules as you're solving for reflections. All right, now you are ready to apply this on your own.